the G. So let G be this set 1, 2, 3, and 4. Let's set the set G be that, and the operation we are considering is the operation of modulo 5 multiplication. Modulo 5 multiplication. So it's multiplication modulo 5. That is, we have this algebraic system where G is the set 1, 2, 3, 4, and the operation here is multiplication modulo 5. So then we want to examine the powers of, we can identify one element A in G. Like for example, a number like 2. We can identify 2 and raise 2 to various powers, each time evaluating that multiplication modulo 5 and see if it will generate all the elements of G. So we want to examine, can write this, examine the powers of elements, the powers of element 2 in G. So in other words, I can continue up there. So in this case now we have identified our A as 2. We want to see if 2 will generate the whole of G. So this element 2 is a member of the set G. Sorry, my throat is not very good. so that now, if we continually raise 2 to integer powers, so if we take 2 to power 1, 2 raised to power 1, and remember we are working multiplication modulo 5 is equal to 2. 2 power 2 modulo 5 is 4. 2 power 3 is 8. 8 modulo 5, sorry, this is 3. 2 power 3 is 8, and 8 modulo 5 is 3. Then 2 power 4 is 16. 16 modulo 5 is 1. This is 1. Then you realize that all these elements that we obtain by raising to the element 2 to various powers is generating actually all the members of G. We have 1, we have 2, we have 3, we have 4. So in brackets I can say that all the results are elements of G. So here I can note and say that all the results of this evaluation of those powers, all the results are elements of G. And therefore the whole set G has been generated by a single element A. So we can say that, let me delete this. So when you have made this observation that up to 2 power 4, you have generated all the elements of the set G. Then now we can say that, and hence we write that the set G is equal to or is generated by 2. It is generated by the element 2. Likewise, we can take another member, another element of G. Say, for example, a number like 3. 3 is in G. So, in other words, we are saying that since 2 has been able to generate the whole of G, then 2 is a generator of G. Let's check for 3. 3 power 1 modulo 5 is 3. 3 squared modulo 5, 9 modulo 5 is 4. 3 cubed is 27. 27 modulo 5 is 2. 3 power 4. 3 power 4 is like having 9 times 9, so 81. 81 modulo 5 is 1. And so we can say that this implies that since we have generated all the members of G, then G is also generated by the element 3. Can we check for 4? Is 4 a generator of G? And 1, is 1 a generator of G? So I would like you to find out whether 4 generates G. So if we take 4 as an element of G, I would like you to raise 4 to various powers and see if you will, the results, each time evaluating the power modulo 5, check if 4 will generate the whole of the set G. And then I'll wait for a check from the public chat what you are getting. So in the same way, try to generate G by raising 4 to some powers and check whether 4 is a generator of the set G. Check if 4 is a generator of G. So it takes 4 power 1 modulo 5, 4 power 2 modulo 5, and so on. So are you able to join? Let's see. I want to create some space here. So what is happening is that we have 4. 4 power 1 is equal to 4 modulo 5. I'm sure this is what you got. 4 squared is 16. 16 modulo 5. You divide 16 by 5, you get 3 because of 15, remainder 1. So you have 1 modulo 5. 4 power 3, 16 times 4 is 64. 64 modulo 5 is 4. 4 mod 5. 4 power 4 like having 16 times 16. 16 times 16 is 256. 256 modulo 5 will give a remainder of 1. So you have 1 modulo 5. So you can see what is happening. Even if you go to 5, 4 power 5, I've worked out 4 power 5 reduces to 4 modulo 5. So you can see there's a pattern there. It's just alternating 4, 1, 4, 1. And so we are not likely to generate the whole of G. We are unable to generate the whole of G. So then what that means is that the element 4 of G is not a generator. The element 4 of G is not a generator. So we can say that therefore G is not equal to that. In other words, 4 does not generate the whole of G. What about 1? If you check for 1, the element 1 of G one is a member of G. So if you raise 1 to various powers, you just be 1. So 1 power 1 is 1 modulo 5. 1 power 2 is 1. 1 power 3 is 1. So it goes on. And therefore G is not generated by that element 1. So you can be asked to find the generators of G and multiplication modulo 5. And so we only have 2 generators because the other 2, these other 2 have failed to generate the whole of G. So we can conclude and say, hence, the generators of G are just 2 and 3. So 2 and 3 happen to be the only generators of the group G. So then we can conclude and say that therefore any group that can be generated by a single element is called a cyclic group. So if you can generate a group using a single element, then we say that that group under the binary operation which is stated is a cyclic group. So that was an illustration that G being that set under the binary operation multiplication modulo 5 is a cyclic group. So we can say that therefore a group that can be generated, a group that can be generated by a single element is called a cyclic group. So we have a cyclic group generated by a single, the given element. So then we can also say that if a group is of order n, if the order of a group is n, and is a generator say X of G. So if the order of a group G is given as N, and there is a generator say X in G, then we say that is now saying that G is generated by that element X. Then the elements of G are as follows. Since now we have said if the order of G is N, that means it has N elements. So the elements of G will be of this, will take this form. We have the identity 1, then we have X, we have X squared, X cubed, it's generated by X. So it is now, we raise X to powers gradually until the last one will be X power N minus 1. So this now forms all the members of the set G, all the elements of the set G, and there are N of them, starting from identity. So the identity there we can say like it's one where we have raised X to power 0, then X power 1, X power 2, power 3, all the way up to N minus 1. And if you recall from our illustration, we were able to get all the members of G by running from 1 to up to 4. Now, if we consider the binary operation of addition, under addition, we see under multiplication, one could not generate G under multiplication. But now when it comes to addition, it becomes, there's a difference because the powers or raising powers when the binary operation is addition means now repeated addition. If you are raising to power 2, you are adding that number twice. If you are raising to power 3, you are adding that number 3 times. So the powers in the case where the binary operation is addition are obtained by repeated addition of the element you want to generate the group with. So we can make a remark concerning that. In terms of addition, we can say that a remark that an additive group that is a group under addition, an additive group, say G, under the operation of addition, is a cyclic group. It is a cyclic group generated by A in G, that is G is equal to that if and only if each element each element A in G is of the form n a for some integer n. So under addition now, a cyclic group will have this feature whereby each element of the set can be expressed as a multiple of the generator, where A is the generator of that set. And that is why now we are saying that this is because under addition, it means now a repeated addition, adding that element several times. And you see, even from algebra, we know that even multiplication can be viewed as repeated addition. If you add the same number to itself several times, then it's as if you are multiplying that number by the number of times you have added it to itself. So let's give an example of, in the case of a cyclic group, an example, just a moment, an example, we shall clear this. To illustrate now a cyclic group under addition, if for example we take G, G is the set with elements 0, 1, 2, 3, and we are performing the binary operation under addition modulo 4. So this system, or this algebraic system, is a cyclic group It is a cyclic group generated by the element 1, since generated by 1, since we can perform repeated addition of 1 to get all the members of G. Like for example, if I take 1 plus, we are adding modulo 4, 1 plus modulo 4, 1 is equal to 2. 2 modulo 4 is 2. Then 1 plus modulo 4, 1 plus modulo 4, 1 is equal to 3. And if I continue this way, 1 modulo 4, 1 plus modulo 4, 1 plus modulo 4, 1. This is equal to 4. And sorry, 4 modulo 4, I think I'm forgetting. 4 modulo 4 is 0. So that is equal to 0. If I continue again, now adding 5 times, we have 1 plus modulo 4, 1 plus modulo 4, 1 plus modulo 4, 1, those are 4, plus modulo 4, 1. This is 1, 2, 3, 4, 5. 5 modulo 4 is 1. And you can see I have generated, I have 1, I have 0, 1, 2, 3. If I continue this, if now I add the 6, 1, 2, 3, 4, 5. If I continue that, I will have 1 plus modulo 4, 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 1, 1, 2, 3, 4, 5, 6. So this is equal to 6. 6 modulo 4 is 2. So I already have 2 there. So I don't have to continue because after that I'll start repeating the same elements. So we can see that therefore G here is generated by that same single element 1. And therefore G is a cyclic group generated by a single element 1. So at this point, we just want to introduce the cyclic group as one of the categories of groups that we of the algebraic systems that we need to mention at this level. But since we shall have another unit of group theory, then that's where we cover all the in details. That's where we cover all the details of groups. So, but we can mention some properties of a cyclic group. This now in passing, since we also discussed some properties of groups. So for cyclic groups, we can say the following. So properties, we just list a few of them. Some properties of cyclic groups. Some properties of cyclic groups. The first one is that every cyclic group is abelian. Every cyclic group is abelian. It is commutative. So that can be shown with, at least now we know what an abelian group is. Property number 2 for a cyclic group is that if A is a generator of a cyclic group, then the inverse of A also is also a generator of the group. So if A in G is a generator, of the group, the generator of this group G under some binary operation, then under multiplication, then A inverse is also its generator. It is also its generator. So if an element A generates the group, then its inverse will also generate that group under multiplication. 3 is that the order of a cyclic group is the same as the order of its generator. Some of this we will cover in more detail in the next level. So the order, because we gave the order of a group as the number of elements in the group. That's why I'm mentioning it here. But now there are, of course, other details we have not discussed yet, so we may not go into too much details of cyclic group. We are just familiarizing ourselves with the algebraic systems. So the order of a cyclic group, the order of a cyclic group is the same as the order of its generator. So these are some common properties of cyclic groups. Another property, the last one, number 4, let me continue it up there. Another property of a cyclic group that is worth mentioning, you can say this is number 4, is that a finite group of order n, if we have a finite group of order n containing an element of order n containing an element of order n must be cyclic. Must be cyclic. So this, when we get to the next level, when we shall be discussing groups in more details, then we will be able to bring out all these properties by illustrating with examples and some theorems. So basically, that's what we would call a cyclic group. It is a group that can be generated by a single element of that set, where the entire all the members of the group can be generated by one element in the set by repeatedly or raising it to integral powers. So another type of groups that I want us to mention, in fact this should be the last one, what you call the permutation groups, permutation groups. And what do we mean by a permutation? By a permutation, we are looking at rearrangements. We look at rearrangements of members of a set. If, for example, you are playing, you have a pack of cards. So you can arrange them in various ways. So when you shuffle them, many times the different ways you can get this same pack after shuffling represents a permutation. So very broadly, we can say that a permutation is actually just a rearrangement of